progress has been achieved during the first full year of Weapon System 107A development. This special report is offered as a quick summary of that development period.
The attainment of an operational intercontinental ballistic missile at the earliest possible date is of vital concern to the national security. In June of 1954, this mission was established by the Chief of Staff in a priority directive to the commander, ARDC. ARDC was directed to reorient and accelerate the Atlas program to the maximum extent that technology would permit. The Atlas, now called Weapon System 107A, was given the highest program priority in the Air Force.
In September of 1955, the President approved a National Security Council recommendation directing that the ICBM be accorded the highest national priority above any and all other programs. The Air Force is developing two competitive technical approaches to ensure the earliest operational ICBM. The XSM-65 configuration is a 1.5-stage ballistic missile integrating 4 major systems and associated subsystems. These include the nose cone, the airframe or body section, a guidance and control system, and the propulsion system, plus the auxiliary power supply and propellant utilization subsystems. The missile is 75 feet long, 10 feet in diameter, with a gross weight of 243,000 pounds, of which all but 19,000 is propellant. The ICBM is designed to attain a speed of over 18,000 miles an hour. It will reach a maximum altitude of over 500 miles, covering a trajectory of 5,500 miles in 33 minutes. To ensure an operational ICBM in a minimum period of time, an alternate configuration ICBM, the XSM-68, was introduced. It is a 2-stage missile, also 10 feet in diameter. The 2 separable stages combined are 6 feet longer than the XSM-65, several thousand pounds lighter, and of a more conservative structural design. The subsystems under development, such as propulsion, nose cone, and guidance, are applicable to either configuration. Therefore, the alternate plan enables the simultaneous development of 2 operational missiles, representing different technical approaches at an estimated increase of 10% over the cost of developing only one configuration approach. In all major performance characteristics, the 2 ICBMs are identical. Late in 1955, the Department of Defense made the decision that an all-out effort be made to develop an intermediate-range ballistic missile. The Air Force IRBM No. 1 will have a range of 1,500 nautical miles and is approximately 1/2 the weight of an ICBM, 8 feet in diameter and only 60 feet long. Except for the airframe, the subsystems used are all derived from the ICBM program. A better idea of ICBM size can be observed in this full-scale wooden mock-up, shown during the development engineering inspection at Convair's San Diego plant on the 25th of October. The nose cone area contains the warhead, stabilizing devices, and the heat absorption sink. The airframe, or main body of the missile, is made up of 2 stainless steel tanks separated by a bulkhead, one for liquid oxygen and one for a hydrocarbon similar to jet aircraft fuel. The propulsion section houses the main booster engines. Since the missile has no aerodynamic surfaces, the gimbaling action of these engines provides the directional control. The operating responsibility for this development program is shared by 3 organizational elements integrated into one operating team under the overall supervision of Major General B.A. Schriever, Commander of Western Development Division. The Special Aircraft Project Office of the Air Materiel Command was activated to provide expedited procurement and other AMC functions at WDD headquarters. In order to gain the services of top technical talent, a unique arrangement was made. A civilian agency, the Ramo Woolridge Corporation, was given a contract to work under WDD as an intimate and integrated component of the project office with a specific responsibility to provide systems engineering and technical direction to all of our contractors. A special scientific advisory committee under the chairmanship of Professor John von Neumann serves as a scientific nucleus to provide technical counsel. WDD has made every effort to acquire the best available industrial and engineering support in the country. The contractors chosen after rigorous competitions have been aligned into closely integrated working teams. The XSM-65 team finds Convair, the airframe contractor, in close cooperation with North American Aviation, the rocket engine contractor. GE's Electronics Division, Burroughs, and the ERA division of Sperry Rand are developing the guidance components. Another division of GE is working on the nose cone, while American Machine and Foundry develops the accessory power supply. The awarding of the airframe contract to the Glenn L. Martin Company in October completed the alternate ICBM team. The result is a close working arrangement between Martin, Aerojet on Propulsion, Western Electric, the Bell Telephone Lab, and the ARMA division of American Bosch ARMA on guidance, and a nose cone developed by the Avco Manufacturing Corporation. The IRBM airframe contract was let to the Douglas Aircraft Company on December 27th. The ICBM contractors who have been redirected to expand present operation in support of this missile include North American, the GE Nose Cone Group, Bell Telephone Lab, American Machine and Foundry, and the MIT AC Spark Plug team. The development philosophy which guides the WDD program maintains these simple principles: maximum testing at lowest possible level, maximum utilization of ground tests, and all components tested have been designed for the operational missile. This amount of testing creates a facilities problem. Prior to the Weapon System 107A program, facilities of the type needed were non-existent. Test stands designed to support captive testing of high-thrust rocket engines have had to be designed and constructed from the ground up. The development philosophy reflects experience based on lessons learned from failures and successes alike in many past Air Force weapon systems, and is strongly believed to be the best way to succeed in minimum time with maximum economy and efficiency. It is believed that the development philosophy being followed will provide a reliable operational weapon system at the earliest possible date. Scenes from recent film progress reports forwarded by the contractors enable us to see some of the development highlights. In the guidance and control areas, progress has been made by GE's Electronics Division at Syracuse on the radio inertial guidance system and on the tracking radar at GE's Schenectady lab. The ERA division of Sperry Rand at St. Paul, Minnesota, and the Burroughs Corporation at Paoli, Pennsylvania, have initiated experimental designs of the logical elements of the computers. An alternate approach to missile guidance is being developed by ARMA in Garden City, New York, by MIT's Instrumentation Lab, and by the AC Spark Plug Division of General Motors in Milwaukee, Wisconsin. At these plants can be seen mock-ups and actual hardware of the all-inertial systems. The latter part of 1955 has seen a rapid buildup of personnel and the establishment of accelerometer and gyro development programs. The equations to be mechanized in the computers were finalized by the Ramo Wooldridge Corporation within the WDD headquarters complex, where both analog and digital computers were available to the system's engineering staff. These accessory power units, developed by American Machine and Foundry at Pacoima, California, will provide power for missile guidance equipment and for ground checkout. These pictures were taken during the preliminary engineering inspection of a full-scale nose cone model conducted at GE's Schenectady plant in early December. An outstanding working group, including representatives of Los Alamos, Livermore, the Sandia Corporation, Avco, GE, Ramo Wooldridge, and the Air Force Special Weapons Center, have in the past year worked out basic agreements on nose cone development. The major items of the nose cone ground handling equipment are shown in this disassembled scale mock-up. This equipment protects the nose cone and facilitates its movement and mating with the missile at the launching site. This is a scale mock-up of the ejection capsule, which will provide flight data of the missile's trajectory. The hard insulating shell of foam and plastic protects the flight data instrumentation against re-entry heating and aerodynamic and impact forces. The nose cone enters the atmosphere at a Mach number higher than 20. Not much is known about Mach 20 flow. The present nose cone design is accordingly conservative. Supporting research will pay off heavily in improving the design. Due to this fact, a very broad program is now in full-scale operation. Materials research is being carried on in several places where high-speed exhaust streams subject the model to temperatures of thousands of degrees Fahrenheit. Resistance heating units have produced temperatures in dense graphite as high as 6,500 degrees Fahrenheit. The Avco Manufacturing Company of Stratford, Connecticut is conducting shock tube tests as one of several simulated flight investigations. Re-entry test vehicles, designed by the Lockheed Aircraft Corporation, are providing important nose cone information on design, materials testing, and heat transfer problems. This full-scale RTV was fired at Patrick Air Force Base, Florida, on December 1st, 1955. Scenes taken at Santa Susana, a facility operated by North American Aviation, will allow us to observe recent propulsion development. Prior to the ICBM program acceleration, North American was the only company in the country developing large liquid rocket engines of the type needed for long-range missiles. A view of the new control center and the recently activated test stand at Santa Susana are shown here. This partially completed area, the Bravo site, will soon be activated. Recently, North American completed a firing of 150 seconds duration of a single 135,000-pound thrust engine similar to the one planned for use in the operational IRBM. The engine was found to be in satisfactory condition at the conclusion of the run, constituting a major propulsion achievement. Here is a prototype booster combination during a recent run. To present a rough idea of the amount of energy involved, these engines are using more than 1,000 pounds of fuel per second. The two booster engines in combination with a sustainer engine will produce a total of 7 million horsepower during flight just prior to engine cutoff. The static propulsion test program provides for over 1,700 test firings before commencing actual launch tests. Aerojet, with facilities at Azusa and Sacramento, has made good progress with the development of their rocket engines. In the last quarter of 1955, they completed more than 100 short-duration firings on single-thrust chamber engines. This work is hazardous and occasionally takes a toll on existing facilities. It's apparent why these test stands must be located in unpopulated areas. Similar eventualities are taken into consideration when planning test firing schedules. Facilities of this type are unique. They have been specially designed and constructed for this program. 6 test stands, each capable of testing 3 engines, are presently either in use or under construction at Aerojet Sacramento facility. This view of Convair's long subassembly line reveals many airframe sections now being fabricated. The flexibility of the half-hard stainless steel is apparent in this section of the bulkhead. The weight of the missile is critical. Each pound saved means about a mile in range. The first structurally complete XSM-65 airframe was processed through final assembly in December of 1955. It has been fully pressurized. These views show the ICBM prototype airframe being taken from the hangar on its special trailer to the new test tower at Convair's San Diego plant. This complete missile tank was built to production specifications with production tools and methods. Ultimate operational responsibility for the completed missile will be assigned to the Strategic Air Command. New construction is well underway on the launch pads at Patrick Air Force Base, which will be used for extensive field testing of the full-scale ballistic missiles. The first full-scale ICBM and IRBM test vehicles are scheduled to be launched from this base in April 1957.